what's the surface area in comparison with finding the volume? Because both are obtained by rotation. But in this case, when we rotate these circles, when we rotate these areas right here, we get that solar revolution. In this case, that's not what we're rotating. In this case, what we're rotating is, well, it's actually this line, is this arc length. When we rotate an arc length, that generates like a really tiny layer, which is the surface area. Of course, I mean, think of a solid body, you know, that the surface area, it's like the amount of skin that solid has. You can think of that, right? And well, of course, there's a few things that we need to specify right here. For example, so that's f of x. However, from the axis of revolution to any point on the graph that we're rotating, so let's call it r of x. That's the radius, you know. So well, when I explain this solids of volume of revolution, when we have especially for the shell method, because this is going to be similar to the shell method. So as opposed to the disk method, it's only upper minus lower times pi, I believe it. You square the function. But for the shell method, you may have seen those like lollipops that if you cut the candy horizontally with a knife, for example, and if you look at the candy from bottom to top, you will see circles for the different flavors, right? Have you seen those kind of candy? I think they call jawbreakers, I think, and then there's these pops called rocaletas. Have you seen those? So that's how they look like. Well, so you can always think of the stick of the lollipop as the axis of revolution, and of course the shape of the candy is given by the function, and then the number of flavors, which is the distance from the axis of revolution to the outermost point on the shape of the on the shape defined by the shape of the candy. Well, that's the amount of flavor, that's the radius. Of course, for the simplest case, they're like the rocaletas, they're circular, and that's easy to see the radius. But of course, you can have like other incredibly weird shaped candy on a stick, you know. So, but that's like the most general case, and that's important to see because that radius right here, in this case, well, for this shape right here, think of a sideways lollipop. So we have it like this. That's the stick, and the radius. The radius from which is the distance from the axis of rotation to any point on the arc length that we are rotating to get that surface area. All right, and as an analogy, let me write down the shell method for the volume. So for the shell method, the most general case was the volume equals to 2 pi integral from a to b r of x f of x dx, where from the candy point of view, r of x is the number of flavors. So the lollipop has x amount or f of x amount of flavors from the stick of the lollipop to the edge of the candy. And f of x, which is, well, typically the top minus bottom, which defines the shape of the candy. All right. Another way to explain these solids of revolutions using the shell methods is to have like an onion as well. You know, if you cut an onion in a horizontal way, you'll see those layers as well, right? So of course, use your preferred example, the lollipops or the onions, you know. And well, so that is going to be the formula for the for finding the solid of the surface area, the area of a surface of revolution. And there's a little typo here that I would like to fix. In the same way, we are going to find the surface area for functions of y. Remember back from Calc 1 when you find those areas and volumes? Well, depending on the setup of the problem, or depending on how you want it to revolve the region about the x-axis, about the y-axis, well, in some cases you needed to redefine a given function of x into a function of y, or vice versa. So this is coming back in surface area, and this is supposed to be a c, a d, and this is supposed to be a y. All right. And well, of course, the graph is very similar to the one on the top. Let me do something pretty quick. And so that's our region of rotation, and this is, this is more or less how it would look like, right, when we rotate. And in this case, the radius, which is the distance, that's important to understand what the radius is. The radius is nothing other than the distance between the axis of revolution and any point on the graph of the arc length that we're rotating. That's given by r, but in this case it's r of y. All right, it's a vertical distance. Okay, so all right, so two cases. Let's look at the different cases. So I have summarized all the cases on the next page, just so you can see the rotation and how to set up the problem. So the first case is when we are using functions of x. Well, if we can use functions of x, and so when we use functions of x, either we can rotate that function of x about the x-axis or about the y-axis. Now, it's this f of x that I have in here. Well, this f of x and the x both represent, okay, let me use a different highlighter here because this is important right here. Depending on how do we go about the rotation, our r of x, which is the distance from the stick of the lollipop to the outermost point and along the shape of the candy, this r of x can be the given function itself or simply x. Okay, how do we explain that? Well, the picture below is going to help us here. Well, so this one right here is a function of x, right? So this one right here, and in this case is rotated about the x-axis. All right, so function of x rotated about the x-axis generates a top minus a bottom point, right? So that's why this radius will be given by the height of the function, which is given by evaluating at f of x, However, on the other hand, if we rotate about the other axis right here, about the vertical axis, the y-axis, well, this distance right here, it's no longer going to give us a top minus bottom, but in a way like a rightmost minus leftmost. However, okay, here I think this is where the lollipop example is going to be a lot useful because, okay, so here's a different color here. Okay, let me see if this works. This is the stick of the lollipop, right? And, well, the shape of the candy, which sort of looks like this. and gets rotated, giving us that candy. In this case, we are going to have a horizontal amount of flavors given by X flavors, not f of x flavors. So that's the case when the rotation is about the y-axis, but still using functions of x. Of course, for using functions of y, we'll have a very similar idea here, where our r of x will be f of y or y, depending on how the rotation goes. All right, but I mean, of course, this is like a lot of symbols, a lot of images. This will make more sense. I mean, it looks like a lot of information for now, but this will make more sense when we do the example. So let's go ahead and do one example. Okay, let me leave this for a second in case that you're still catching up with this. All right. And well, I didn't have a picture for the functions of y, but I mean, you'll see. Actually, for these notes, I have one example of it, so you can see how we set each of them and why. Okay. So let's look at the first example. So number one, we have this function, the curve y equals to 4 minus x squared, and they're giving us the limits in this case. We don't have to find anything lucky for us. They're giving us the limits between -1 and 1, and this radical function is actually a piece of an arc of this circle. You'll see why. Let's find the area of a surface obtained by rotating this arc about the x-axis. So number one, let's see. X squared plus y squared equals 4. Whenever you see this function right here, this equation right there, what does that represent?
A circle.
Circle, what else? Let's get more details about this circle.
With the radius of 2.
It's a radius of 2, and it's centered
At the origin.
at the origin. Great. All right, so let's draw a circle of radius 2 centered at the origin. Okay, so that's a 1, 2, 1, 2, 1, 2. Okay, this would be the whole picture, right? However, we don't want the whole thing. Number one, that radical function that they're giving us at the beginning of the problem, number one, this is, recall that this x squared plus y squared equals to 4 is the same as saying, well, on the one hand, y squared equals 4 minus x squared, and y equals plus or minus the square root of 4 minus x squared. All right? The fact that we have a plus and a minus, it's meaningful. The plus sign, the positive function, gives us the upper semicircle, and the minus describes the lower semicircle, right? Okay, but in this case, so we don't want the lower semicircle, we only want the upper semicircle because, well, this is implied to be a plus on the one hand. Also, well, they're giving us another condition here. The other condition is that the limits of integration have to go between -1 and 1, not from -2 to 2. So let's take that also into consideration. So let's erase. Okay, let me erase. And instead, I'm gonna draw this arc right here. Whoops. But okay, never mind. So that's the only region or part of the circle that we will rotate. All right, now This is being rotated about the x-axis. That is, it's going to do this, right? This is not my x-axis, and the rotation goes like this. That means it's going to look like this. And it's gonna, and the other end is gonna look like that, right? Using a little bit our imagination. Have you seen those Parmesan cheese? I mean the one that they imported from Italy, those big rounds that are flat on the side, well, flat on the bottom and the top, and kind of circle from the edges. Well, you can think that that's what we're doing. We're finding the area of a Parmesan cheese that has this dimension. So that's pretty much what we're doing. All right. What else? So in this case, well, the rotation is about the x-axis. The distance between the axis of revolution to any point on the graph will be given by the following, and this is the trickiest part. So this is what defines the rest of the problem in this case. The r of x is going to be any point that lies on the function f of x. All right. So I will be doing this for every single problem that I'm going to do for this section, just so you can see how do we set it up and why in some cases the r of x is f of x and why in other cases the r of x is just x, not f of x. You'll see. So, okay, let's set up the problem. Let's write down the formula. I would start with the formula. So in this case we use uppercase S for surface area. That's 2 pi. Integral from a to b of the r of x, the radius, times the square root, in a very similar to the arc length, 1 plus f prime quantity squared. All right. Did we take the derivative? No, we still need to take the derivative of the function. Let me do it over here. All right. So let's go back. Take the derivative. So that's a y equals to 4 minus x squared to the 1/2. And well, using, in this case, we need the chain rule. 1/2 times 4 minus x squared to the negative 1/2 times the derivative, which is negative 2x. And this is the same, well, the 2's reduce, the negative goes in the front, and we can write that as a radical in the denominator. All right, so let's see. This will be, okay, so negative x over 4 minus x squared to the 1/2, which is negative x divided by the square root of 4 minus x squared. So that's going to be our derivative here. Let's highlight just so you can see where am I going to put it. Okay. Well, this is going to block your vision a little bit. Let me use a different color to highlight this one. This one will be here. All right. Okay, so let's set up the problem again. The other piece of information is that r of x in this case will be our f of x. So this is 2 pi integral from a to b f of x, the square root of 1 plus f prime quantity squared with respect x. Okay, so s, rather big S, that's a 2 pi, the integral from negative 1 to 1 of f of x, and in this case the function f of x, which is the square root of 4 minus x squared, times the square root of 1 plus the square root, or not the square root, rather the derivative of the function which we found before. That's negative x, oh come on, negative x over the square root of 4 minus x squared. And I know the integral is not looking pretty, isn't it? But don't worry, this will reduce like really nicely, you'll see. So on the one hand, okay, let's simplify the quantity inside of the radical. Okay, so this will be okay, let me see if I can make this a little smaller. Yes, much better. So this is 2 pi, the integral from negative 1 to 1, square root 4 minus x squared, square root of 1. Okay, quantity, negative quantity squared becomes positive, and then x to the second power, that's going to be an x squared. What's going to happen with the denominator? Radical squared, radical cancels the square, and that's okay, I think I will need a glove or something here so my hand doesn't touch the other. Four minus x squared, oh come on, dx. Okay, so let's see what we're gonna do about this one. So again, just like we did with the arc length problems, okay, I think I'm gonna need to rewrite the whole integral to leave a space, and this will be s equals to 2 pi, the integral from negative 1 to 1. We will deal with the limits of integration, by the way. I'll show you why. So that's 4 minus x squared times the square root of 1 plus, let me leave some space over here, more space, x squared over 4 minus x squared dx. And then the whole thing right here, divide by 1, and we need at least common denominator, so we can combine these two fractions together, so we can get the expression in terms of only one single term. That way we can use the square root property to take square roots, instead of, because we cannot take the roots of a sum or difference of terms, only factors. All right, so the LCD, we get it by multiplying and dividing by 4 minus x squared. Right? So in this case, 2 pi, the integral from negative 1 to 1, square root of 4 minus x squared times the square root of the numerator. It's going to reduce like really nicely. So this is 4 minus x squared plus x squared divided by 4 minus x squared. So do you see how these two x squareds cancel out? All right. That's going to leave us with the following. That's 2 pi, integral from negative 1 to 1, square root of 4 minus x squared over this times the square root of 4 over 4 minus x squared. And this one is going to be really, like I mentioned before, this one reduces really nicely. We may now take the square root of the numerator, take the square root of the denominator. What's the square root of 4? 2. What's the square root of 4 minus x squared? Well, the square root of 4 minus x squared. But did you see what's going to happen here? Like I promised, this one was going to reduce really, really nicely. Now, there's another thing that I would like to do here. So, 2 times 2 pi, that's 4 pi outside. Oh. Four pi times the integral from -1 to 1, and with respect x. So not even a variable is inside of the integrand. Now this is the thing. You might want to take advantage of the symmetry of this shape. Do you see the shape? Okay, let me scroll it up a little bit. It's perfectly symmetric about the y-axis, so changing the limits to make our work a lot easier. So this will be 4 pi times the integral from 0 to 1, but in this case, okay, let me use a different color. From 0 to 1, but multiply by 2. In other words, we're integrating from 0 to 1 and multiplying that by 2 by symmetry in a way that one of the limits of integration is 0, and that we take advantage of the symmetry properties, because when we compute functions at 0, what do we get?
0.
Most of the times we get 0, so that simplifies our work a lot. Of course, if you want to leave it like this, that's fine, but that's something I prefer to do. Take advantage of that symmetry property. And well, what's the integral of the x? So that's going to be 8 pi x from 0 to 1, and 8 pi times 1 minus 0, which is 8 pi units. All right. Questions about it? All right, guys, looking at the clock. Oh, it looks like this is perfect timing, well, except for 1 more minute. Okay, guys, so we're gonna take